Well, Professor Clements, another example of speed of light and how it could be used in a calculation. Let's set up a little scenario. A hypothetical astronomer on a planet around another star. There are many planets that have been found around other stars, so we don't know of any life on them. Hypothetical astronomer. This astronomer does not know the size of the orbit for the planet the astronomer is writing on. We're going to assume the orbit's circular. The physicists on the planet are pretty advanced, though. They've determined the speed of light, 3 × 10⁸ meters per second, and they have good craftsmen making clocks that can keep accurate time for half of the orbit of the planet at least. As the astronomer looks at a distant planet, the astronomer finds that there are moons of that planet that regularly disappear behind the planet and then reappear. And that process can be observed over and over and over. As it is observed over and over, and if we take a situation where this distant planet is very distant, it doesn't move much in its orbit, while the astronomer's planet is moving quite a bit. So that moon, as it passes behind, as the astronomer writes down the times of disappearance, they become later and later than they should be, than they're expected to be. The moon might take a few days in its orbit going around the planet, a few days and some odd hours, but it's a regular pattern. But as the astronomer's planet moves in its orbit around the star, the astronomer notices that there's a delay in the timing of the eclipse, of the disappearance of the moon around the distant planet. And when the astronomer's planet is halfway around its orbit, that delay is accumulated up to 18 minutes. So the eclipses are later than what was expected by 18 minutes. Can we use that information to find the radius of the orbit of the astronomer's planet? Well, yes, we can. This was done and reported in 1676 for the case of the Earth. So I'll try to make somewhat of a sketch of what's happening here, not to scale, but here's the orbit for the astronomer's planet around the central star. And we're going to first observe here when this situation of this distant planet, and there's a moon going around, and that distant moon, get this here, that distant moon's moving into the shadow cast by that distant planet, and that's the timing that we're interested in. We want to see that occur over and over, and we want to watch as the astronomer's planet moves over to this position, half of the orbit. At this time, now there's a delay of 18 minutes. When the astronomer writing the planet at this position sees this moon disappear, it's 18 minutes later than expected, and there's been a gradual increase in the delay as the planet moves back here to position 2. So what could cause this observation of the delay? Well, the moon here is in a regular orbit. It keeps going around and around and around. Nothing to do with the position of the planet back here that would cause the speed of this moon to change, nor the size of its orbit. What could be happening regarding light coming from this moon to the position of the planet here, or the position of the planet halfway around its orbit? And you might be exclaiming right now, "Eureka!" It's because there's a travel time for light across the diameter of the orbit of the planet. The light, as it goes across here, requires some time to move from position 1 to position 2. If we had an astronomer at position 1, they would see the eclipse happen at the proper time. But the position 2 location for the observer, the eclipse is delayed by 18 minutes. Well, the diameter of the orbit here, that distance, can be calculated by the rate of light traveling across here and the delay time. So we know the rate, 3 times 10 to the 8th meters per second, and we know the time, 18 minutes. Is that all I have to do? Just multiply those two numbers? No, we must do a conversion factor. We have meters per second for the speed of light. So we have to get rid of minutes and bring in seconds. We want to get rid of minutes, so I'll put 1 minute down here in the denominator and 60 seconds up in the numerator. Now the minutes cancel, the seconds cancel, and we'll be left with the size of the orbit, the diameter of the orbit. You should do this calculation, pause the video if necessary, but multiplying these values together, I came up with 3.24 times 10 to the 11th for the diameter of the orbit for this planet. And we know that the diameter is equal to 2 times the radius. So we have the diameter number, we divide that by 2, and I found a radius of 1.62 times 10 to the 11th meters. Is there anything we could compare that to? Well, yes. The radius for the Earth's orbit is about 1.5 times 10 to the 11th meters. So this is a reasonable result. There are a lot of different size of orbits, of course, for planets around stars, but it is a reasonable result. And this was done in the late 1600s by astronomers and gave an estimate of the speed of light, actually, as they had a rough idea of the size of the Earth's orbit. So doing distance equals rate times time, the astronomers in the late 1600s, Roemer, had a rough idea of the diameter of the Earth's orbit, the distance, measured this time delay for the satellites of Jupiter, and then calculated the speed of light. Came up, I think, about 2 times 10 to the 8th meters per second, but it was a ballpark number. Here we're using the speed of light to calculate the diameter of the orbit and then the radius. So keep practicing.